So today we are going to introduce a new concept called fluid dynamics. So here we are going to introduce computational fluid dynamics. You see, computational fluid dynamics, or CFD, is a science of predicting the fluid flow. Okay, we are going to predict the fluid flow, heat transfer, even mass transfer, chemical reaction, and all the related phenomena. So it is done by solving mathematical equations. You see, these sort of physical phenomena are governed by partial differential equations. If you've been to in bachelor studies, you have seen that partial differential equations are very good at governing different physical phenomena. So by solving these mathematical equations or these partial differential equations, we can actually predict these things. So this is the work of CFD, or computational fluid dynamics. We will talk about CFD in brief today, and later on we will go in much deeper sense. Okay, so actually CFD uses numerical method to solve these mathematical equations, or we can say partial differential equations. So it's just there is an image for the visualization of wind turbine using CFD software. You see that there are different lines, streamlines, or we can say a method of visualizing fluid flow through the wind turbine. Okay, so next one, next is now types of approaches to solve fluid dynamics. So there are three sort of approaches to solve fluid dynamics. First one is experimental fluid dynamics. In acronym we say it as a EFD. Similarly, second one is analytical fluid dynamics, or AFD, or third one is computational fluid dynamics, or CFD. So in case of experimental fluid dynamics, we obtain the solution of fluid dynamics by conducting experiments. You see, if you have been to aeronautic engineering or mechanical engineering, you see our labs are full of these apparatus such as wind tunnel and a lot of things. So these apparatus are actually very costly, they are very expensive, and they are some sort of required a skilled human power or a lab operator. So you see, experimental fluid dynamics is quite costly, and it provides an actual way to solve these physical problems, even though it is costly. Second one is analytical fluid dynamics, where we solve differential equation which governs the fluid dynamics. You see, the differential equation governing the fluid dynamics are quite harder to solve analytically. So therefore we simplify these partial differential equations containing two or more variables into ordinary differential equations by certain assumptions. You see, this method is applicable to simple fluid dynamics, simple problems of fluid dynamics, where there are suitable assumptions can act to convert these partial differential equations into ordinary differential equations, but it is not going to work all the time. So the most important approaches to solve fluid problems is computational fluid dynamics, or CFD. So here we obtain the solution of partial differential equation on a discrete grid using numerical process. You see, why we choose numerical process is because analytical way is very difficult, or sometimes we cannot approach the answer, and even though we can approach answers of some sort of differential equations that are partial in nature, but it takes a lot of time, lot of energy, lot of money. So computational fluid dynamics uses numerical process. Yeah, numerical process can give a approximate value or answer or result. So we can get answer up to desired accuracy, whether we not get actual answer, but up to desired accuracy. So we don't care about a minimum error that we are going to possess using numerical process. So next one, where we will go, need of CFD. So we shortly introduce what CFD is. Now it is necessary here. What is the need of CFD? We need to explain this. So you see, the fundamental basis of all sort of fluid problems are Navier-Stokes equations. If you have been to fluid mechanics classes, you have heard about Navier-Stokes equations. These equations are very good at approximating or modeling the physical behavior of fluids into mathematical model. Just ignoring the turbulence, all sort of fluid problems can be modeled in terms of Navier-Stokes equations, though it doesn't have any features or any idea about turbulence, but it includes the viscosity. So they are very good at approximating or modeling the physical phenomena in terms of mathematical models. So these equations are the fundamental basis of all sort of fluid problems. You see, these are the partial differential equations that guide or that models any sort of fluid problems. So if we limit ourselves to just incompressible flow, okay, where viscosity is constant, even though we limit ourselves with incompressible fluid and constant viscosity, we still end up with these equations. If we consider in a compressible fluid and a variable viscosity, then there is a long lines of equations, so it will be rather much more complicated. So even we limit ourselves in incompressible fluid with constant viscosity, we get this much amount of equations, though they look very scary, very huge, but this is also after suitable assumption that the fluid is incompressible and with constant viscosity. Now in practice, there is no general analytical solution to these equations. So complex fluid problem have almost impossible sense of solving by analytically. So from 18th century to till now, we are preferring numerical method over analytical one. So this is an important approach. This is an important conversion from analytical one to numerical one, because it is almost impossible to solve some general fluid problems. We can solve simple side of fluid problems by analytical one, but it is nearly impossible for complex problems. We use computational power to numerical process. Why numerical process is preferred? One of the best reason behind it is computational power. Okay, if you have about Euler's method, you see, we need some sort of iterations. As big as our iteration is, the approximate or close answer is we get. So here, for iterations or for long number of iterations, we use computational power. We are not going to do by ourselves. So using computational power, since we have computational power, we can solve by iterative process. I'm giving you just an example using Euler's method, but there are several other way also. Just for the reason of easier comprehension, I'm going to give this example. So like in Euler's method, we solve any differential equations by increasing more and more iterations, getting closer and closer to the actual curve or actual graph. So in the same way we use computational power for such iterations. Okay, hope you get it. So actually you need to get some sort of previous informations about computational fluid dynamics and approaches, so you can get this video more beneficial. Okay, so CFD is preferred because of its low computational cost, high speed, ability to simulate multiple and complex fluid problems. Okay, and next one is working of the CFD. So here analysis begins with a mathematical model of the fluid problems, physical problems. Conservation of mass, momentum, energy must be satisfied throughout the region of our interest. So we create a region of our interest for analyzing the fluid flow, for getting necessary data. So we separate or we create a boundary around our interest of fluid flow region to get our required measurements. So simplifying assumptions are made in order to make the problem more trackable, such as steady state, incompressible, inviscid, and 2D flow. Okay, so if you want get actual result, then you may not require to simplify, but for the sake to help computer, because computer also lag here, because computer, yes, CFD is a vast thing, multiple millions and thousands of computations are going round and round. So we are supposed to put less pressure on computer, so we simplify. If it is a steady state, why to make rely computer on computer? So we let it to solve. We state it is a steady state. The fluid is almost incompressible, we state it is incompressible, inviscid if it has no viscosity, and if there is no reason to work with height or anything, any dimensions, we can only consider 2 dimensions. So it will be more easier for computer to solve, or we can also save our time and as well as computational cost. So appropriate boundary conditions are set for the problem. You can see the image has a domain for fluid problem in the elbow. Okay, so so CFD applies numerical method called discretization to help the approximation of the governing equation of the fluid mechanics and the fluid of region to be studied. So a discretization is a method for approximating the governing equations. You see, we divide the region of our interest into millions of tiny blocks, and we consider that there is no variation in the fluid parameter within the block. The collection of these cell is called grid. So why we divide it, the block into small millions of tiny regions? Because if we consider a dot, there are infinite dots, and we cannot consider this much. So we divide the block for the sake of our computation. So we divide a block and consider a block as a single entity where there is no variation in any fluid parameters such as pressure, velocity, temperature, any sort of parameters. As small our block is, the way our result will be better. So CFD code works in 3 steps, and these 3 steps are pre-processing, solving, and post-processing. So let us look about it also. So you see, we have seen in chart the working of the CFD. For this video we are going to just explain this only, and our upcoming video will provide you detailed information about working of the CFD and different sort of things so related to fluid dynamics. So it is very very interesting topic, and it is eye-catching. It grabs your attention by its own. So let us talk about a sort way, a brief way of working of safety codes. So first one is pre-processing. So in this stage, you create a geometry that you want to analyze, or you want to study the behavior of fluid across it. Then second condition, second steps after it is meshing. Meshing means, I've already told you, we divide a body into millions of tiny blocks, and these blocks or grids where fluid properties are invariant, and the collection of these grid is called mesh. So dividing of a whole body into smaller one is called meshing, and we specify the fluid property, whether it's a water, whether it's a liquid, whether it's a gas, whether it's any sort of fluid that comes under the software. In the similar sense, viscosity is different fluid property and parameters, and then we set up the boundary conditions. You see, what boundary condition are is what's outside the boundary, where there is a wall, where there is a solid, or whether what is the pressure at the inlet, what is the velocity at inlet, all sort of things that you know about the thing you want to study. So second steps is solver. So there are three sort of solving, that is finite difference method, final volume method, or final element method. So we use finite volume method here, and we will talk about these three later on. If we are going to talk about these things, then our video will be so much big. So here are different softwares, popular software such as ANSYS. Within ANSYS, there are two softwares that are providing some fluid solve related problems, and these two softwares are Fluent and CFX, and most of the popular one is Fluent. Both are Fluent and CFX come under the category of ANSYS. CFX was sold after by CFX company to ANSYS, and these softwares are pretty much simple and similar one, but the only difference is the way to solve the problems. Okay, third one is post-processing. After post-processing, you want to visualize, so it includes all the things that you want to visualize the result, such as animation, part tracks of the fluid particles, contours, line plot, vector velocity, and different one. So thank you for watching this video, and this is my first video in this YouTube channel, and hope you enjoy it. Later on, I will try to make more and more videos on fluid mechanics and different mysteries on sciences. Thank you.